session here with Michael Byington. I asked him how I should introduce him today. He said he's a tree climber. He has done a lot of stuff, so that describes him. But I let him introduce himself a little bit more if he wants to. But he will talk about today unit-style networks for time series feature identification.
Thank you. I'm Michael Byington. I'm working for a small startup company doing pipeline inspections, not pipelines like data pipelines, but pipelines as in physical oil and gas pipelines. The things that I've done with neural networks in this job are things that are quite literally only interesting to me and to absolutely zero other people. But because neural networks generalize to many, many different problems, I'm hoping that I can kind of outline a case study of ways to think about problems that do not neatly fit into computer vision, natural language processing, and the things that you immediately think of when you think of neural networks. To get started, I want to tell you a little bit about the context of the problem. So the pipelines that carry fluids that you think of long-distance transport pipelines came into existence in the United States in the 1860s. They were the primary competitive advantage of a company called Standard Oil, which made the Rockefeller fortune. John D. Rockefeller is arguably the richest American that's ever existed, and that was largely because of pipelines. From the 1860s to the 1960s, the strategy was, if it leaks, there's a problem. If not, ignore it. There wasn't really any alternative. In 1964, I believe it was, a company called Tuboscope created a magnetic flux leakage device, which used a lot of magnets, and you would stick this device inside the pipeline, push it with fluid, and it would record data. And from that data, you would try to infer things about the quality of the pipeline and hopefully fix problems in the pipeline before they resulted in environmental disasters. This is essentially the technology that's in use today, primarily. The main problems with these is they are enormously expensive. To run an MFL tool through your pipeline, you're looking at minimum $100,000 per survey. For a high-quality survey, you're looking at $1 to $10 million just to do the inspection. That's not to fix anything that's wrong. That's just to get data on the pipeline. And if you talk to pipeline operators, you will discover that these things don't work very well. They very often report that the pipeline is in pristine condition only to have it fail a week later, or that the pipeline is horribly corroded and must be replaced. You go dig it up, and you find pristine pieces of pipe. It's not 100%, but awful like that. But in extreme cases, these things fail quite rapidly. The other big problem these have is there's 100 years of pipelines that were installed with no thought that you might want to stick one of these in the pipeline. So this thing cannot go around. It bends, diameter changes, valves with bore sizes that are smaller than the existing pipe. And so there's a giant collection of pipelines that are known as unpiggable lines. These things are colloquially known as pigs. So in the 2010s, we started trying to invent devices that could get us at least some data on unpiggable lines. The picture on the upper right is the device that the startup company that I work for champions. It's called a Piper, and it's a free-floating little tennis ball-sized device that you ship off to a pipeline operator, so our people are never on site. They drop it down their pipeline, they ship it back to us, we read the data off a USB stick, and then we try to analyze it and tell them something useful about their pipeline. That's our business model. We've got a number of sensors on board this device, and the easiest use case, there are several use cases for this device, but the easiest one to understand is you have a leak in your pipeline. We go floating past the leak, and we can hear it. It sounds like water gushing out of a hose if the leak is large. There's a whole bunch of cases in which we might not be able to hear a leak, but in the cases where we can hear a leak, it's pretty unambiguous that that's what's going on. There's not a lot of other noises in the line that you might confuse with a leak. The problem here is we know when we passed by the leak, but that does not tell you where the leak is. We know when the survey started and ended. We know the length of the pipeline. But if you just use start and end and interpolate between, you're going to get a horrible time to timed conversion, because pipeline operators do not operate pipelines at constant flow rates or constant pressures or constant anythings. It is all a disaster. We use as much information as they'll give us: bends, any metallic hardware that we can see in the magnetics data, diameter changes, which we can see by changing velocity, elevation changes, which we can map to changes in the pressure data that we collect. So the time to distance mapping is complicated. But what's important to understand is that we need to identify all the joint locations in order to get an accurate distance, because for the most part, they're going to work with regularly lengthed pieces of pipe. And those regular sized pieces of pipe, if we can identify joint locations, we can get a much more accurate distance than we can by any other method. The other problem is joint identification is very manual and very expensive. And this is what I was hired to solve 2 years ago. This is a very short piece of pipe. This is probably somewhere between 800 and 2,800 kilometers, I would guess. This whole survey took like 25 minutes. And this is just the magnetics flux inside the pipe. Our devices don't have any magnets in them. We're not applying any electric fields or magnetic fields. This is just what you measure if you drop a magnetometer down an oil pipeline. The reason this is hard to do is because some joints are pretty obvious, right? I'm sure that nobody here thinks you need a neural network to identify these joints. You could write it just SciPy find peaks, and you could get a perfect location for all of these peaks. But joints are very heterogeneous. If you look at pipeline magnetics data enough, it starts to look more like image detection. I know it when I see it. I'm looking for a pattern that's relatively regularly spaced, but I don't exactly know what that pattern is going to be. Sometimes it's spikes, sometimes it's increases in the oscillation frequency, sometimes it's sudden offsets. There's a million different things that a joint could be, but we know that the joint is the only thing that's going to show up that frequently and at that regularly spaced an interval in the pipeline. So this is where I got hired to try to design a neural network that would pick these things out. So how many people here are familiar with neural networks? Oh, that's most of you. OK, sorry. I might have a little more information than you need. How many people here don't get invited to parties because they design overly complicated architectures and nobody else wants to hear about them? OK, so that's a couple of us. We're going to be friends. I'm going to run through Neural Networks 101 in a couple slides. Hopefully I don't bore anyone too much. Neural networks are really simple. Nobody is too intimidated by them. Basically, when someone says fully connected layer, you just think matrix multiplication. If someone says convolutional layer, just think that's a convolution operation from mathematics. There's nothing complicated or special about it. And a pooling layer is a traveling window that's taking the max or the average or the min or some other simple operation. In practice, it's always the max. Just assume a pooling layer is a max pool layer. If someone's doing something that's different than that, it's their obligation to tell you that they're being weird and why they're being weird. When you draw out a neural network graphs, the red dots represent numbers. On the left side, that's your input. On the right side, that's your output. In the middle, those are the hidden layers that you generate. You have a weight that connects each input layer to each sequential layer. And if you draw this out in a graph, you have drawn out a series of weights that are well captured by a matrix. You multiply W1 by vector 1, you get vector 2. W2, x2 gives you x3, et cetera, et cetera. Now, for those of you who have paid attention during your algebra class, you might notice that all of these matrices, they collapse, and you don't actually need that many numbers. This is something of a problem in designing neural networks, but it's a problem that's really easily solved. This is why we have activation functions. You apply a function to each scalar in the hidden layer, and as long as that function is nonlinear and differentiable, everything is fine. In practice, you want the simplest possible activation function because it will make it computationally easy to compute. If you want to get more performance out of your network, you're going to get much more bang for your buck by changing the size of the layers, the orientation of the layers, the number of layers. If you spend time trying to change activation functions around, it's very unlikely that that's going to improve the performance of your network relative to doing these other things. The simplest thing that you can compute is a ReLU. and that's why almost all modern networks use ReLU activation functions. There are some exceptions, but in general, that's how it's done. Convolution, it's a lot easier to explain a convolution by stealing a graphic from Wikipedia than it is for me to talk about it verbally. It's a traveling frame that gets multiplied and sums across a subset of your data, and then it moves across the entire the entire input to generate the output. The nice thing about convolutions is they allow you to learn about features of your data independent of where they occur in your data. And they're a computational way to connect large layers together. If you were to do this with a fully connected layer, instead of having 9 weights, you'd have close to 1,300. So this is an excellent way to learn things independent of where they can occur within a homogeneous data set. Convolutional neural networks are the go-to standard for almost all computer vision tasks at this point. So if you were going to design a neural network that identified happy frogs from sad frogs, you would take all the pixels in your neural network. This is probably a bad neural network to do this because this is pictured as fully connected layers. You'd probably want to do this with convolutions. You have a whole bunch of weights in this neural network. You have to define some way of telling the neural network how well it did at deciding whether that was a happy frog or a sad frog. You do this with what's called a loss function. The only thing that's important about a loss function is that it's differentiable. And when it goes down, that's good. Other than that, you can define any loss function you want. In practice, it's very difficult to define new loss functions that are useful. So when you're doing a classification task like this, cross-entropy loss is the go-to standard. It is beyond the scope of the talk, but you're just going to have to take my word for it that it is possible to computationally fairly efficiently compute the derivative of the loss function with respect to every single weight in this graph. And then it is possible to update every single weight in this graph by moving every single weight a very small distance in the direction that lowers the loss function for a given collection of input data. So in order to build a neural network, you start by just defining your graph, randomly choosing some weights to start with. These are there's a little bit more to it in the sense that if your distribution of weights doesn't conform to certain things or certain constraints, then you might get something that never converges. But most neural network libraries do that for you automatically, so you don't have to worry about it. It's randomly chosen to start with for our purposes here. You select a small subset of your data. You can augment that data, stretch or compress, or do something that changes it slightly so that the neural network can't memorize it. And then compute the loss function over this small subset of data, update all the weights, and when you go through this process, this is called training your neural network. The cool thing about deep learning is the first step is almost always remove almost all of the context from your problem. This is nice because once you've solved the problem, you've solved many, many, many problems. And then you have cause to celebrate. So UNet is a neural network that came out in 2015 that revolutionized a collection of problems called segmentation problems. And it was designed to do this, which is to say, taking a micrograph of cells, pick out all of the pixels in that micrograph that are cells. We're going to do the same thing. We have the X, Y, Z components, and so we have a one-dimensional image, and we are going to identify all of the joints in our one-dimensional image. This is the analogy that I'm trying to stress because I think this is the most critical part of my talk. If you can see an analogy between these two things, you can use the very powerful solution that was published in 2015 to solve this problem that nobody else cares about. And it's very useful if you're working for a startup company and you're hired to be the only in the world who cares about this thing. Unfortunately, there's a couple small complications. If you take this network as it's written and you convert all the two-dimensional convolutions to one-dimensional convolutions, nothing works. The network doesn't train. And the reason it doesn't train is because there's a concept in convolutional neural networks called a receptive field. When you have fully connected layers, this doesn't apply. But because the convolutions are only looking at a small subset of the data between each layer, when you stack layers on top of each other, the final node is only being influenced by a subset of the input pixels. The authors of this paper gave us a very convenient equation for a collection of convolutional and pooling layers to define how large this receptive field is. And when you apply this to UNet, and we're just looking at the encoder side, which is the left-hand side of the network. I wasn't quite sure how you would interpret that on the transposed convolutional layers going up the decoder side. But if you're just looking at the encoder side, you're looking at a receptive field of 140 by 140 pixels. For inputs that are 500 something by 500 something pixels, you're looking at a third of the image. That's more than enough context for UNet to figure out if something is a cell or not a cell. Unfortunately, if you just change the two-dimensional convolutions to one-dimensional convolutions, you still only have a receptive field of 140 pixels. 140 pixels is not enough context to make a decision about that point as to whether that is a joint or not. But because that equation gives us a way to change that, if you just increase the strides and the kernels of the convolutional and pooling layers, you can very rapidly increase that context. And I designed something that got that context up to over 10,000 pixels. And that is enough context to determine whether each of those points is a joint or not a joint, because you can see several joints in that context. You can find periodic features. So that's the key to making all of this work. Data augmentation is critical when you're working with small data sets. We do not have access to the kind of data that you have at Google or Facebook. We have very small data sets. This can all of the training data can fit in the RAM on my desktop. So we're trying to get as much out of it as we can. In order to do that, we're trying to change the data in ways that don't affect the features that we're looking for, but prevent the neural network from memorizing specific features of our input data. In this case, we can compress or stretch the data in the x direction, which would correspond to our devices moving faster or slower through the pipe. There's no particular reason they had to move at the speed that they went through the pipe. We can compress or stretch our data in the y direction. If the magnetic field was slightly more powerful in the pipe, we would just as easily be able to recognize the joints. So this stretching and compressing doesn't change anything. And then we can take the mirror image of our data, because that would correspond to just traveling through the pipe in the reverse direction. What we ended up with was 12.6 million weights, 111 surveys that contain 91,000 labeled joints. But because of the data augmentation, we were able to show this network 40 million labeled joints in training, and it never once saw the same joint twice. There was always some augmentation applied to it, and because those augmentations can vary in magnitude, it's very easy to get essentially an infinite number of training examples. That doesn't mean you have infinite power, but it does give enough variability that this will learn incredibly powerfully and generalize extremely well. The end result is that if you feed this piece of data into the neural network, you'll get Y1 and Y2, which is the no joint and joint labels in this fashion. If you take a softmax of that, which is just this equation right up here, you get spikes at all of the joints. And this, you can always run a peak search tool on and recover a joint list. So that, I think that's pretty cool. Now, that is an example of how to apply this to something nobody here cares about. But it did really well. There's a number of ways to take the thing and make it more general and apply it to a broader category of problems. For example, sometimes we run attached to the back of a cleaning pig. The acceleration gyroscope might give you some information if the cleaning pig fits tightly. That piece of rubber will hit the joints, and you can integrate this information and find a whole new neural network that works in the same way as the old one, but is much more accurate for pig runs. Transfer learning works on these extremely well. If you freeze the first and last couple of layers and then train for a few thousand cycles, you get wonderful results. Cardiology in one slide. I'm looking for examples of things that other people might care about. And I was trying to come up with ways that I could apply this network, transfer learning on this network, to something that was more broadly interesting. It should work on anything that you are doing that involves one-dimensional time series data for which you have a lot of labeled data of the things that you want to identify. In cardiology, this is a heart. I hope everyone has one. Hearts are a little more complicated than I realized, but you have these two chambers up top that do a little squeeze to fill the two chambers at the bottom, and the two chambers at the bottom push the blood out. The one on the right shoves blood just into your lungs, and the one on the left shoves it into the rest of your body. There's an electrical system in your heart that controls contract the top, contract the bottom sequence. Basically, you have a pacemaker, that's your SA node. The electrical signal travels across the atria. Your atria contract about 1/10 of a second later. After a delay in the AV node, your ventricles contract and push the blood on. This is how cardiologists try to figure out what's wrong with your heart. They stick a whole bunch of electrodes across your body, and they measure the electrical signals that come through this sequence of fibers. I'm not a doctor. Please do not hire me to be your cardiologist. What you end up with is, depending on which one of these you're looking at, you should be able to see most of these features in most of these different combinations of electrodes. A P wave, which is the contraction of the atria, the top chambers. The QRS complex, which is the contraction of the ventricles, which are the bottom chambers. And the T wave corresponds to the repolarization of the ventricles. The atria obviously polarize, but they're much smaller, and they do so at almost the same time as the QRS complex, so you can't see the repolarization of the atria typically in an EKG signal. I downloaded a bunch of EKG data, and I applied this transfer learning technique using the neural network that I trained on pipeline magnetics data. And this is my one and only test or validation set. But I'm pretty proud of it. Like it found all the P waves, the Q waves, et cetera, et cetera. I'm not going to say that this is the best data science anyone's ever done, but I am going to say that it's a really interesting proof of concept and that this does generalize to much more than pipeline magnetics, and that's why you should take me seriously. I did this by taking my neural network. I froze everything but the first and last layer. I had maybe 400 of these that I labeled manually, so very, very small set. Trained it for about 1,000 training cycles using all the same data augmentations as the pipeline data except for the mirror image because your heart doesn't pump backwards, I hope. If you do that for 1,000 training cycles this way, and then you unfreeze the middle of the network and you train for another 1,000 cycles, you can recover this result. Doesn't take very long. The longest part of this was manually labeling 400 EKG signals. It was raining on Saturday. I didn't have anything better to do. I really like data. I collaborate with a lot of different people. So for reasons that I will explain off camera if anyone's curious, I have an enormous amount of data of asphalt deflecting on a variety of conditions when heavy things roll over it. You might be curious about where the rebounds in that data occur because rebounds in asphalt have a lot to do with failure modes of asphalt. Again, same procedure. I took my neural network, I froze all but the first and last layer and trained it for 1,000-ish cycles, repeated the training with the network unfrozen for another 1,000 cycles, and I was able to identify all the rebounds in all of the test cases that I used. The only thing that's tricky about this that you would want to keep in mind if you were trying to reproduce this yourself is that the neural network is learning about peaks and valleys and spacing based on the spacing between data points. That's its sense of time. So if you don't upsample your data so that the peaks are spaced in time by approximately as the same number of data points, the transfer learning fails completely. The inputs that we were shoving into this neural network are 81,000 data points long. The EKG data was 3,000, 4,000 data points. So that had to be significantly upsampled in order for that to work. The same is true with the airport or the runway deflection data. Didn't work very well when I tried to do it with earthquakes. The main reason being that earthquakes are, or I believe the main reason is that earthquakes are kind of a broad signal. They're not discrete points that you're trying to identify, and as such, transfer learning pretty well failed. I also only had a couple hundred labeled samples of these micro earthquakes that I was trying to apply this to, so I gave up. I got a little demoralized there. But if you had a lot more of this earthquake data, I'm very positive that you could make a neural network that identified your micro earthquakes by training it from scratch. I think there's a lot of cool stuff to learn here, but what I'm hoping that you'll take away is that you can use neural networks to do more than just image detection, natural language processing, and all the traditional things if you're able to see analogies between different types of problems. You can apply the solutions that are out there to very, very unusual applications. And with that, I will open the floor for questions. If you don't want to ask me questions in front of everybody, you're welcome to ask me privately. I love talking about neural networks, so I hope that I am not intimidating in any way.
Thank you for the talk.
Welcome.
Very naively, per your premise, my first thought with these tennis balls is, well, is there must be some constraint that's preventing you from getting like geolocation data attached to these, and I'm curious what that constraint is, because
yes, there's a number. The first one is we struggle with battery life in these devices. The second one is you're in a steel tube, you're in a Faraday cage. That makes it really tricky. Fourth, you're underground in most cases. Like we run subsea lines that are thousands of meters below the surface. And all of that combines to, it's really hard to get location data. There are situations where we get a little bit more location data via kind of unconventional means you wouldn't think about. And these are collectively known as above ground markers. So they'll stick giant magnets on the side of the pipe or just above the pipe, and they'll hope that you can see that signal, or they'll stick little woodpeckers on the side of the pipe. And so it's just a metal device that's tapping on the pipe, and you'll hear it as you go by, and it gives you a location. You know at that time you were at that spot. The market that we're going after are places where you can't use any of that stuff. And there's all kinds of reasons that you can't use any of that stuff. I mean, there's expense with installing it. There's we run in areas of the world where it's not safe to install it, where you can't send people into the area because there's wars and instability and places where you just really don't want personnel there for liability reasons. All of that means that we're trying to do it with the least amount of information we can.
Hi, thank you for the talk. So I'm not like a neural network expert by any stretch of the imagination, but
well, then you might have enjoyed the slides about the neural network.
I guess, can you just talk a little bit about like what you mean when you say you like freeze a couple layers with the transfer learning and things like that, and just because I'm not as familiar with transfer learning. I understand reinforcement learning a little bit, but
Okay.
Yeah.
Yes. When you are doing transfer learning, you don't have to do this. Transfer learning just means you take an existing collection of weights with an existing architecture and you're going to try to apply it to a new problem. You're going to do the same thing where you've got a loss function. You're going to give it some training data, and then you're going to update weights, and then you're going to give it some training data, and you're going to update weights. When we say freeze the network, we're just not going to bother updating any of the weights in the layers that I've grayed out here. You're only updating weights in the first and the last layer, or the first and last couple layers. That makes the transfer learning work better. You get much higher performance out of that because initially the derivative is going to tell you to change all sorts of things throughout the entire network. And if you're trying to move in a very different space, intuitively it makes sense that you would want to change the input to look more like what the neural network was originally trained on. And so if you do this freezing where you're doing several training cycles without updating any of the weights in the center of the network, you get better results. So that's what I mean when I say freeze layers of the network.
Thank you. Also, just out of curiosity, what's the length of how long can some of the pipelines be?
Oh, longest pipeline we've run, I think, is on the. I know we've done pipelines that are over 100 kilometers. I don't know if we've gone over 120. Generally, we're moving at about 1 meter per second or so, and we've got a 24-hour runtime. So that gives you kind of an upper bound on what we can do.
Hi, thanks for the talk. I work with PPGs signals as part of the sort of domain, which are similar to EKGs in the sense that they can represent a heartbeat event.
Know much about cardiology. I made that up.
I don't know that much either, but yeah.
So I have no idea what you're measuring, just to be clear.
It's an arterial pressure wave, but it's like you get a something that's and they have common use cases that would be synonymous with EKGs. There's some overlap in the science surrounding them, but anyway, my question was. Drawing on your experience using this network for event detection in the pipelines, how was the performance? Were there any issues you ran into with noise? Because that's really the problem with event detection in PPGs. If you have a clean signal, it's really actually quite easy to get event detection. But the thing is, it's like you never have a clean signal. And so I'm curious if you could comment on that.
Yeah, so we've got very large amounts of heterogeneity among what these signals look like. And some of them, we can't see welds. We occasionally get pipelines, probably 5% of the pipelines that come in, we open up the magnetics and we're going to manually identify welds, and we just don't know what to do. We don't know what we're looking at. My experience has been that anything that we can manually identify, so we know that there is a feature there that we can manually detect, we can train a neural network to do it if we've got at least 150,000 labeled examples of what we're looking for. Getting those labeled as examples is the hard part, and it's not clear whether the human eye can't see it or the information's just not in the magnetics. Like, you can imagine it's possible that in some of these pipelines it's not there. But there's no amount of noise that we've been unable to see through with a neural network if you can manually see through it with your eyeball. I don't know that there's any fundamental reason for that. The easy one to come up with is, at some point, just the information's not in your data. But we haven't proven that the information's not in our data. We've just proven that we haven't been able to detect anything else. I'm not sure if I've fully answered your question, but I tried.
If you could fully answer my question, I've got a job proposition for you.
We have maybe time for one more. Okay.
And while you're getting over there, we are always hiring. Just shameless plug if anybody really wants to play with pipelines.
Cool. Thank you for the talk. It was great. Is there any sort of analogy to like the Shannon-Nyquist theorem that ties like the window length that you're looking at, that the neural network is capable of seeing, to like what scale of feature you can detect?
So it depends on how much I guess the question is, how much context do you need to see the feature? And that's going to be very feature dependent. So that's going to be very application dependent. In our case, if you zoom in what you're looking at, your manual labeler can't identify a joint if he or she is looking at less than one spool. Spool is a single manufactured piece of pipe. Less than one spool of data, it's very hard to tell because a lot of what you're looking for is a repeating structure. If we don't give the neural network the context of that repeating structure, performance drops very significantly. I don't know if there's anything about that can generalize to other applications, because I can imagine that a cardiologist does not need to see multiple heartbeats to recognize a QRS wave. And therefore, I would assume that a neural network does not need to see multiple heart rates to identify a QRS wave. I think there you're looking at something that's much more application dependent than any simple answer that I could give you.
Cool, thank you.
Okay, thank you very much. If there are further questions, feel free to touch base with
I'm
Mike.
very sociable. You can talk to me anywhere.
Thank you.